Okay, so in yesterday's class we learned two really important theorems which were actually proved using this substitution theorem. Okay, the first of these, what we wanted to do was, let us say we said we have two networks, some n and n1. Okay, we said let n consist of a bunch of resistors, basically linear elements, okay, plus some voltage sources, plus some current sources, okay, and maybe even some control sources, okay, and that network is connected to some other network N1, okay, through these two 1 and 1 prime, these two terminals, right? And we said that this N1 could be anything. We did not place any restriction on N1. The only restriction was on N, right? We are saying N should contain these these types of elements. The other restriction we made was that any control sources in N should not depend on outside voltages or currents, right? So in this particular case, it should not depend on voltages and currents in N1. So what I want to do is I want to replace this network N, okay, by something simpler across these two terminals 1 and 1 prime. Okay, across these two terminals 1 and 1 prime, I want to replace N by something else such that it looks exactly the same. Electrically, it should look the same. When we say electrically it should look the same, what do we mean? So the voltage behavior and the current behavior should be the same. Is that clear? And we said we can analyze this using superposition. So what we said is we first applied substitution theorem. In this particular case, we started off with substituting the network N1, okay, between 1 and 1 prime using a current Ix, okay, and then we said we will apply superposition for this new system, okay. We'll apply it in two steps. In the first step, we would make Ix to be 0 and excite the network with all its internal voltage and current sources. Okay, that is this portion. What does that mean? If we set Ix equal to 0, we will get an open circuit between 1 and 1 prime. And if we calculate Vx1, that will give you the open circuit voltage of network N between 1 and 1 prime. Correct? The next step, the next part of the superposition theorem, okay, the superposition is you take the same network N but de-energize all its voltage and current sources. If you have any voltage sources, you're going to make the value 0. In other words, short circuit any voltage sources inside N. If you have any current sources, you're going to make the value of the current source to be 0, okay, and that means open circuit all current sources. And then you're going to apply this Ix and find out what the Vx is across it, okay. That would be related in this manner. You know this network is made up of some linear resistors and some control sources, okay, and that will give you some resistance RTH, okay, which we called the Thevenin resistance. Similarly, the original open circuit voltage was called the Thevenin voltage VTH, and we know that the actual voltage Vx has to be a linear, has to just be the sum of Vx1 plus Vx2, okay, and that is nothing but VTH minus Ix times RTH, and therefore the equivalent circuit for the network N across 1 and 1 prime is nothing but a series combination of VTH and RTH. Okay, this is called the Thevenin equivalent of the network N. Okay, and this theorem, the fact that you can replace any network, okay, between two terminals by a simple series combination of a voltage source and a resistance, this theorem is called Thevenin's theorem. So what all did we use? We used superposition principle, we used substitution theorem, right? Superposition theorem and substitution theorem was used to prove Thevenin's theorem. Any questions about this? About Thevenin's theorem? Now the next step, if you want to see what the behavior of N1 is when you connect N to this, all you have to do is energize N1, excite N1 with just a series combination of VTH and RTH. The state of voltages and currents inside N1 will also not change. Okay, because the same voltage Vx and Ix have been created across these two terminals, 1 and 1 prime. Is that clear? Very good. Now there is no need to be partial to the substitution theorem. You applying substitution theorem with just the current source. You might also want to do it with a voltage source. We have seen substitution theorem said you could replace it with either the voltage source or the current source. Okay, so you do it using a current source, you will get Thevenin's theorem, which is Thevenin's equivalent circuit. Now you can choose to put in Vx instead of N1, okay, across 1, 1 prime. Again apply superposition. Okay, you set Vx equal to 0, energize N using all of its internal voltage and current sources. If you set Vx equal to 0, you are going to create a short circuit between 1 and 1 prime. Okay, so you will get what is the short circuit current, okay, through 1, 1 prime. We will call that Ix1 to be In. Okay, then the other part of the superposition is you de-energize all the sources, all the independent voltage and current sources inside N. Okay, that is basically N is nulled. You are going to apply Vx here and find out what Ix is flowing. Okay, that will clearly be some form of resistance across these two terminals, because now N has no independent voltage and current sources. Okay, so that resistance is called Rn. Okay, now if you had to superpose these two situations, okay, you will get an equivalent circuit which will look like this. Ix will be nothing but In minus Vx by Rn. Okay, it is very important to maintain the directions of the currents or the voltages in the earlier case. And the equivalent circuit for this kind of system across 1, 1 prime will be a parallel combination of this current source In with this resistance Rn. Okay, what is this Rn? Rn was the open circuit resistance of the nulled network N. That is the same as RTH. Okay, RTH is equal to Rn. Okay, that's number 1. And if this system has to have the same equivalent circuit between 1 and 1 prime, what that means is you also have to have this relationship has to hold. VTH has to be equal to In times Rn or In times RTH. Okay, so if you know the Thevenin equivalent, you can find out the Norton equivalent and vice versa. Okay, now finally I ask you to look at one last thing. There is one small difference between the Thevenin's equivalent and the Norton's equivalent. What is that? Anybody think about this? So I have a network N. Okay, this is N. Okay, and I take two versions of this. I take two black boxes. Okay, inside this I place the Thevenin equivalent. This is 1 and 1 prime. Inside this I place the Norton equivalent. Okay, I just calculate what the Thevenin equivalent of this network N is, what the Norton equivalent of N is, and then I just recreate those two by just using a voltage source and the resistance and a current source and a resistance. Right? This is 1 and 1 prime. Will there be a difference between these two? If you had to find out the difference between these two, what would that be? Yes. Okay. Perfect. That's the answer I was looking for. First of all, electrically there will be no difference. Very clearly it is meant to replace across 1 prime. Both the Thevenin and the Norton will replace the network electrically, okay, perfectly well and in an identical way, right? You excite the network N1, some other unknown network N1 with either the Thevenin or the Norton equivalent, you will get exactly the same state inside N1. However, the state of this guy, okay, voltage and current states will also be identical. However, note that, as she pointed out, when you open circuit 1 and 1 prime, okay, the Thevenin equivalent is open circuited, okay, whereas the Norton equivalent does have a loop here across 1 prime. So what does that mean? So voltage and current, as far as voltage across 1 prime and current through 1 prime, right, there will not be any difference. You connect anything else externally, there won't be any difference. But very clearly, what kind of impact is this going to have? Any ideas? Yes, somebody said the answer here. Somebody just mentioned the answer, I heard it. Who was that? Sorry. Yeah, that's right. So you can see clearly that the power dissipation here is 0. Okay, the power dissipated here is non-zero. Okay, that is a big difference between the Thevenin and Norton equivalents. So if I just gave you a black box, very clearly the temperature of the black box, okay, having the Norton equivalent will be higher. Okay, it will be dissipating power. So there is a physical way of finding out which one is different. Very clearly there is no electrical way of figuring out which is which. That much is clear. Because remember that the power for a voltage source or a current source comes from some chemical energy. Okay, the electrical energy is actually transformed chemical energy. We are not tracking that. We are not tracking the chemical energy. Okay. Fine. Any questions on Thevenin or Norton equivalent circuits? So let us say I have an example prepared for you guys. So let us say this was the network N. Okay, I have some combination of voltage source, current source, some resistors. How will you find out the Thevenin equivalent of this? How will you find out the Thevenin equivalent of this? Huh? Anybody? I didn't expect this after just reviewing what Thevenin equivalent circuit is. Anybody? How will you do it? How did we figure out VTH and RTH for an arbitrary network? Huh? Yes, find the open circuit voltage. So open circuit, do not connect anything between 1 and 1 prime. Find out the voltage. Okay, that would be VTH. Right? You find out the resistance between 1 and 1 prime. right, with the voltage and current sources nulled, that will be the Thevenin resistance, right? Okay, do it now. I'll quickly do this. I want to find out RTH. How do I find out RTH? I have to null the voltage and current sources. Okay, how do I null this voltage source? I short circuit it. So I have 2 ohms. I open circuit the current source. Okay, and I want to find out the resistance between 1 and 1 prime. Okay, so since I've shorted the current source, what is the resistance looking in here? I have two ohm resistors in parallel, so that's 1 ohm. Okay, what is the resistance looking in here? I have 1 ohm in series with that 1 ohm, so that's 2 ohms. Okay, so the overall RTH is again 2 ohms in parallel, which is 1 ohm. So RTH is very straightforward to write down for these kinds of simple networks with nice values. Okay, what about VTH? This is the open circuit voltage across 1 prime. How would you do this for any general network? Would you sit down and start solving KVL, KCL? Maybe that makes sense, right? Maybe for a very complex network. But if you have a lot of sources, what makes sense is to apply superposition between those sources. Okay, apply each source in turn. You will be able to reduce the network. Okay, find out the voltages across, each resistor or the current through each resistor and so on, and figure it out. And finally, add all of them, right? Apply each source, whether it's a voltage or a current source, in turn, and add all those voltages. Okay. So let us quickly do this. I have only 2 sources here. Okay, now let us say I get rid of this guy. I don't have this anymore. How do I find out the voltage here? How do I find out the voltage here? So I have some whole bunch of currents here, right? I have 2 sets of currents here. This is a fairly easy network to solve. What are these 2 currents? Suppose I call these 2 terminals 2 and 2 prime. Okay. On the right side, what do I have? I have 1 ohm in series with 2 ohm, which is 3 ohms, right? And on this side, what do I have? I have 3 ohms in parallel with 2 ohms. Okay, so I can find out the input resistance across these 2 nodes. Then I can find out this current Ix. I'll call it Ix1. The minute you know Ix1, you can figure out how it splits among a parallel combination of 2 ohms and 3 ohms, right? So the thing is, the fact of the matter is, you will need to practice, solving these kinds of networks. Okay, what happens when a current tries to enter, a known current tries to enter a parallel combination of resistances, right? How would you know how much current flows in each one? So if I tell you I have a known current, okay, let's say 1 ampere, entering a parallel combination of 2 1 ohm resistances. What is the current through each one? Half, right? So I have 0.5 amperes through each. What if I told you one of these was 2 ohms? Which is 1 by 3, which is 2 by 3? So in that case, you will have 2/3 ampere and 1/3 ampere and so on. Right? You will have to learn, how to do these things quite fast. Otherwise, even simple networks will take you a long time. Okay, that is the moral of the story. Try to get hold of, if you get the textbook which we prescribed at the beginning of class, you can do all kinds of problems, all the practice problems at the end as a supplement to the tutorial. I'll give you the final answer. I don't want to spend too much time. I'll give you the final answer. I want all of you to go and try it out. Next class, on Tuesday's class, we will I hope by then all of you would have done it, because anyway you have the exam, right? So, okay, so the what you should be getting is, of course, RTH, this open circuit voltage should be 5 by 4 volts. That should be your answer. You can go back and check this out. Now, just a quick point about, okay, can you please quiet down? You can discuss the problem later. So, last class, one of you came up with a degenerate case, or a very special case of for the substitution theorem, and in that case it turned out that, it looked like the voltage numbers were unknown. You will find similar kinds of degenerate cases if you try to apply Thevenin's theorem also. Okay, and I'll give you an example. Suppose this was my network N. This was my network N. Okay. What is RTH? What is the Thevenin resistance? What is the Thevenin resistance of this network? Who said 0? Who said 0? Somebody said 0. Why is it 0? What do you do when you find out Thevenin resistance? You null all the sources inside and find out the resistance between the terminals. What do you do? How do you null this current source? You open it. What is the resistance between 1 and 1 prime? It's infinity. Okay. What is ETH? What do you do when you find out VTH? You find out the open circuit voltage, right? What is the open circuit voltage? Is it unknown actually? If I take a current source and leave its terminals open, what voltage do you think will be developed across these two terminals? Infinite, right? You try to pass any current through through a wire that is open, right? It will develop an infinite voltage. Okay? So what we are saying is we have, but this is the Thevenin equivalent, but you can clearly see that this doesn't make sense. What we are saying is this I naught will still be equal to VTH by RTH. That's what we are saying. So in this case, you can clearly see it doesn't make sense to talk about a Thevenin equivalent of a degenerate case like this. Similarly, by the way, however, it makes sense to talk about a Norton equivalent. Okay, a Norton equivalent for this network, what is that? What is it? It is just the current source itself, right? RTH is same as Rn, which is infinity, which is open, there is nothing there. So between 1 and 1 prime, you just have an I naught. Okay. Similarly, you can take the case of a voltage source. Of course, the Thevenin voltage will be the same as the voltage source itself. Okay, the Norton current source will look like it doesn't exist. It will give you a degenerate case again. Okay. Any questions on Thevenin and Norton equivalent circuits, or Thevenin's theorem and Norton's theorem? Okay, so the next theorem we are going to look at is what is called maximum power transfer theorem. So let us say I have a network N. Actually, there is one, before we go to maximum power transfer theorem, there is one last thing I wanted to say about Thevenin's theorem. So far we have been looking at examples where you have resistors, voltage sources and current sources. What do you do if you have dependent sources? How do you find out VTH and RTH? How do you find out VTH? VTH. It's open circuit, you don't null anything. Right? It is the open circuit voltage. But how do you find the open circuit voltage? Of course, you have independent voltage and current sources and also dependent sources and some resistors. With all of these combined together, you solve the network, you analyze the network and then find out what the open circuit voltage is. Of course, you will take into account these control sources also because they will modify the voltages and currents through the inside this network and therefore they will modify the open circuit voltage. That is fairly straightforward, I would think. Right? What do you do about the Thevenin resistance? How do you find out the Thevenin resistance? So you are going to make the independent voltage and current sources zero. What do you do about the controlled sources? However they change. Suppose you have a network of resistors and you can take this case. Suppose I null 3 volts and 1 ampere. What will happen to the voltages and currents through these resistors? They'll go to 0, right? If I had some control, let's say I had a voltage control current source. The voltage was the voltage across one of these resistors. What will happen to those sources? The current source will become 0 and look like it becomes an open circuit. But is that right? So in other words, what I am asking is, when we had simple cases, right, just independent sources and resistors, I just told you, find out the resistance between those two terminals. So it is very easy to reduce the network of resistors between those two terminals until you get RTH, right? The minute you have control sources, you cannot do that anymore. So how would you figure out RTH? Let's go back to the definition of RTH. RTH is defined as the resistance across terminals 1, 1 prime after nulling all the independent voltage and current sources. Okay, that is the definition of RTH. Now how would you use this definition to find out what RTH is for any arbitrary network? So you null this and what else do you do next? If I give you two terminals and I tell you I want to find the resistance across it, what would be the obvious way of doing this? Okay, apply a voltage and apply the voltage and measure the current, right? So I would apply a test voltage across these terminals and I would find out what test current it takes. Okay, there will be some current flowing through it and I can calculate R Thevenin as V test by I test, right? This is the obvious way of doing this. All I have access to are these two terminals 1 and 1 prime. Right? I apply some test voltage, some known test voltage, measure what current it takes and find out what VTH by ITH is. And in fact, you could have done it for this particular example. You could have done this for that example. It was so easy that it was much faster to just look at it and figure out what these resistances are. But if you apply a test voltage across 1 prime, measure the current and divide the two, you will get it. Alternatively, okay, you could also apply a test current, measure the voltage developed across 1 and 1 prime, okay, that will also give you the resistance, okay. You could also do this, okay. Both will give you the same result, of course. Now the point to note is that the minute you excite the network with a V test or an I test, okay, what happens? The dependent sources will matter, okay. The Thevenin resistance will be a function of whether you have dependent sources or not. Is that clear? Because the minute you apply a V test, you are going to have some set of voltages developed inside the network, and those dependent sources are now energized. Is that clear? So if you have dependent sources, this is the right way to approach the problem. Okay, back to what we wanted to study next. This is what is called maximum power transfer theorem. Okay, I have some arbitrary network N. Okay, again the same thing, resistors, independent voltage or current sources, and maybe even control sources. Okay. Now I am going to connect some load resistor to this across 1 prime. Yes.
So before that, in the
Previous case, yes.
So if you can, so the answer shouldn't matter based on what actual value we pass, right? What actual current we pass or what.
It will not matter, because what? Why is that? The minute you have nulled the network, it is a linear network. Okay, the minute you have nulled the network, it is a linear network, because why is that? Even dependent sources, okay, the proportionality constant is a resistance, a conductance, or a constant. Is that clear? It is the minute you have nulled the sources, it is a linear network. So it will not matter whether you apply 1 volt and measure the current. You apply 10 volts, you will get 10 times the current. Okay, it will not matter. You can take any test voltage or any test current that you apply. Yes.
Sir, even suppose we take that 1 and 1 dash across the resistor. Suppose.
Across the resistor?
In the network.
Yes, okay. No, what we have actually done is to disconnect that resistor which was originally connected between 1 and 1 prime. We are replacing the network across 1 and 1 prime as this.
No. Inside the network, if we are taking two terminals as one.
You can take any two terminals and call it 1 and 1 prime. Yes, correct.
Now what if any dependent sources, voltage or current sources, depends on the current between that resistor?
Okay, maybe I'll say this again. Give me just a second. So when we started off talking about substitution theorem, okay, we just pulled out one resistor. We had the network N. Okay, we pulled out one resistor from that N, and we said that can be replaced by either Vx or Ix, Vr or Ir. Okay. Correct? And similarly, we can even find the Thevenin equivalent of the network across 1 and 1 prime and so on. We can do all kinds of things. Now, I can just take the network, leave the resistor inside, and just take out 1 and 1 prime. I can do that also. Okay. If I do that, what will happen to the Thevenin? There is no more substitution theorem here. I can just find out the Thevenin equivalent across 1 and 1 prime. That will obviously be different because now I have the original resistor as part of the network earlier. So in this case, what I would have had was, if I had replaced I would have got some RTH1, I would have got some VTH1 across 1 prime. I would have connected R here, I can calculate what current is through R, what voltage is through R. What will that be? It will still remain VR and IR. If I do this, I'll get some RTH2, VTH2. I have not connected anything else across 1 prime, but I can choose to connect anything else externally and figure out what happens. These are two totally different cases. I think that answers your question. I hope it does. It does, right? In one case, when we started off assuming substitution theorem, we pulled out R and called it something separate outside this. We are trying to replace the resistance with some voltage source or current source. Okay? In the second case, we are trying to replace the overall network across any two terminals with an equivalent network. We just used substitution theorem to do that. That is all. Okay? So now I have this network N. I am taking any two arbitrary terminals 1 and 1 prime. Okay? They are two terminals of interest. That is all they are. I am connecting some resistance RL, some load resistance RL between 1 and 1 prime. Now I am going to try to achieve a very specific objective. I want to deliver as much power as possible to RL. Okay? The objective is to maximize power delivered RL, but of course the minute you have an objective you need to have something variable. Okay, that variable is going to be this RL itself. Okay, I am going to change RL. Let RL be the variable. I am going to change RL and I want to find out what value of RL will give me maximum power in RL. How will you do that? Maximize. So first of all, write down the expression for PL, which is the power delivered to the load. What is that? What is PL? VL times IL. Or you can write it as, since this is the resistor, you can write it as V squared by VL squared by RL or IL squared times RL. You can write it in many different ways. So what is PL here? How do you simplify this? Can you simplify it first of all? You don't know anything now. What we want to do now is to simplify N. How do you simplify N? Thevenin's theorem. Okay, or Norton's. By the way, you can do Norton's also. It will give you exactly the same condition. We will take Thevenin's theorem. So this is RL, this is RTH, this is VTH. Okay. So what is PL? What is the expression for PL? So what is VL? It is RL VTH by RL plus RTH times what is IL? VTH by. Okay, this is the expression for PL. So this is VTH squared times RL by RL plus RTH the whole squared. Is that right? Okay, what do you do next? You want to maximize power transfer. Okay, so you would differentiate this with respect to RL, set it to 0 and so on. You will get the value. What, anybody has seen this before? What is it? RL equals RTH. Has anybody seen this before? Okay. So this RL equals RTH will give you maximum power in the load. Okay, I'll let you do that differentiation and so on in the as part of the homework. You can do it in many different ways. Okay, I could take this. Let me do it in a slightly different way. So PL is Vth square times RL by RTHT whole squared. Okay, so I am Vth squared by RTH, okay, into correct? I have just taken one RTH outside the square, okay, Vth squared by RTH times RL. I pull out root RTH out of the square, okay, so I have root RTH left here and I have RL by root RTH, and I can also rewrite this 1 by correct? I can rewrite it in this form. What is this? Root of RL by, in the denominator, I only have, I have two terms depending on RL. If I want maximum PL, I want that term to be minimized. Okay, when is that term minimized? It is of the form x plus 1 by x. Yeah, it happens when x is the same as 1. That is when it is minimized. Okay. So this will give you RL equals RTH. Okay, you can do it in many different ways. If you differentiated and set it to 0, that would have given you the same answer. This is called maximum power transfer theorem. Okay, so we'll just start off on one topic so that I can give you something to think about just in 2 minutes. Suppose I take any arbitrary graph. Okay, now we are done with maximum power transfer theorem. We are moving on to the next topic. I am taking any arbitrary graph. Okay, it consists of some certain number of branches. Okay, so I can define the branch voltages with a certain convention. V4, V5. Okay, I can also define the branch currents. And in what direction do I assume the branch currents? Based on the passive sign convention. The minute I draw out the voltage signs, okay, I know which directions to choose the currents. Okay, so I have I2 in this direction, I3 in this direction, I4 and I5. Okay. Now, suppose I try to find out sigma Vk Ik across all branches. What will this be? 0. Why? Can you prove this? Suppose I asked you to prove it. Huh? Okay. So, is it true? See, you are basically saying energy has to be conserved, but remember that if you have a battery inside, there is some chemical energy being converted to electrical energy, right? So what we are talking about here is only the electrical power. Okay, so in some sense what you are saying is right. It seems to make sense, right? If something is consuming power, something needs to be generating power, right? That's what we have seen. Okay, if you have let's say take a voltage source and put a resistor across it, the resistor is dissipating power, the voltage source is producing that power that is being dissipated. But if I gave you any arbitrary combination, can you prove this? Huh? Okay, so this will be your homework for today. I'll also tell you it can be proved purely using just KVL and KCL. Okay, so this is your homework for today. Okay, on Tuesday in the next class, we will see how to use this result to prove yet another theorem. Okay, for networks, for any arbitrary network. And that theorem is extremely interesting and you'll see why.